Baji. Here is Baji. Here's my Fuji Baba. Hi, Fuji Baba. All right, we will get started. Who is ready for tonight's live? Who? Who is ready for tonight's live? Cats and physics. And actually, today we're going to cover astronomy. In just a second, I will be introducing our topic. I'll let people join. In the meantime, thank you so much for being here. Welcome, welcome, welcome to the live. If you're seeing this as a video upload later on, welcome. And thank you for watching. Please do watch till the end and leave us a comment. Thank you so much. Oh, Baji. Oh, Baji, Baji. Oh, Baji, Baji. See, we're ready with gold standard whey protein, which is going to be the phone stand pretty much. It will support my phone camera. BJ! Hi, BJ. How are you? Ooh, let's check that the stove oven is off. Indeed, all the dials are in the off direction, up and vertical, up and vertical, up and vertical, off, and off. Very good. BJ, Happy New Year. Hi. So yes, indeed, this gold standard thing is the phone. See, I'm going to put my phone right there when I rotate the camera. I've got my water ready. I've got my laptop ready so that I can share the live and look up things on Google as needed. And then tonight, we're going to use this book that we have been using for reference, Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. Suji Mama. Where's Baji? Oh yeah, I think Baji will make himself visible in just a second. Let me go and turn off this gigantic light, which is on my face. I don't think that it is helping too much. I think that's more normal. Hi! Hello, my friends. Welcome to the live. Welcome, welcome. If you want to keep seeing Suji, here she is. Welcome to the live. I'm going to share the live. BJ, tell us how you're doing. Hi, Swati. Swati says, hi, sister. I'm Swati. Welcome, Swati. How are you? BJ says, haha, Happy New Year. Here is Suji Mama. Here is me, the mother of Suji, Fuji, and Baji. Swati says, I'm fine, sister. Oh, very nice. Old says, I love you. Oh, thank you so much. How are you? How is everybody doing? We are just now getting started. Welcome, welcome. Harper, hi. Hello, Harper. Hi, Old. Old says, Kitty. So last night I was very tired and sorry about the slow live last night. It was a little bit slow and sort of droopy and sleepy, and that's okay. BJ says, I'm going to take a nap. Ha, see you. Denny says, honey, WSP honey. Swati says, vlogs, content, challenge, sister. Okay. You're very beautiful, says Old with the skull shapes. Thank you so much. Thank you everybody for joining. Welcome to the live. We're gonna be talking about a lot of stuff tonight and we will get started, but I wanna look at all your comments and chat messages first. I have school tomorrow, so I can't stay long. Harper Pitt. Okay, that's totally fine. You look high out of your mind, says Miles. Hello, Miles. Trish says, hola, hi. Hi, Trish. Hola, Trish. Swati says, stuffed newspaper. That sounds really hard, Swati. I'm not sure that I would do that challenge. On this channel, I mainly love what am I even saying? On this channel, I mainly cover kitty cats, books, and physics. So the topics that we generally cover are just generally chatting, hanging out with the kitty cats, and generally topics in physics and astronomy. So And actually, we have also been covering a lot of physics, astronomy, cosmology, as well as sort of a history of science, especially focused on the 20th century and now coming towards more current times. Hello, Swati. Hello, Trish. Hello, Old. Hi, Francis. Hi, Miles. Hi, Harper. Hi, Old. Hi, Denny. Hi, BJ. And I think I've said hi to everybody. If I did not say hi to you and I missed your message, then say something now so that I can say hi to you. Can you show us the cats? Here are the kitty cats. Here's one. Here is Suji Mama. There is Fuji. And where is Baji? I think Baji is using the bathroom right now. Hi Trish. Girl, you look young. Thank you. Fred says hi. Nice cats. Thank you so much. Okay, so I never shared the live. As usual, I get distracted by all your chat messages. Which is totally fine. Reese, hello. Swati says, mythology sister, are you interested? I am actually pretty interested in mythology. If you want to share some mythology facts with us in the chat, then feel free. Reese says, hello guys. Hi Reese. Trish says, bye, I gotta go, sorry. Okay. No need to be sorry. You can just go. Han Gabrielle says, it is so cute. Thank you. Mohammed says, hey. Fred Blanau says, it's a myth. Trish says, okay. Yes, you can stay, you can go, and have fun either way. So I am gonna, let's see. Hi, ZAFNYT. Hello, what is your name? My name is Baji, the Handsome Cat's creator. And Baji, the Handsome Cat mother. What is your name? Fred says, nice smile. Okay, cool, thank you. Wait, are we in a different room today? No, it's the same room. I'm just sitting at the counter where I've been sitting for a few lives now. Instead of on the couch, I am at the counter on my bar stool. So you've seen me here. You've seen me here in the past. In the past too, you have seen me here. See, I'm standing up. See, there's the cat tree. Just wanted to adjust my dress. Definitely a different room. Doro. Are you adding to the controversy? Hello, Doro. How are you? I know you were sick, so are you better now? I'm looking at my face here. My eyebrows look weird. Oh, get on couch. It's comfy. Hey, Doro. Babu is my nickname. Hi, Crazy Sick Wine. I thought I saw you. Crazy Sick Wine. Hello, my brilliant friend. How art thou, lovely woman? Thank you. I am good. How are you? Thank you for joining the live. Yes, and I'm good. Thanks for asking. Hope you're well. Thank you. Tony says, okay. I was so tired last night. Hey, Reese. Sorry, I was doing my homework. That's okay. You can continue to do your homework while you do this live and whatnot. So, in fact, this live may sound and feel a lot like homework. So, because we're going to be getting down to business today. Yesterday, we had a very, so I'm sharing the live again on my channel. Who knows what I'm typing? Join us and chat and say hi. That's the thing. Hi, Iggy. Thank you. Crazy Sick One says, well, my insomnia is back tenfold. Not doing great, but I'm here for you always. Thank you so much for being here. So Crazy Sick One, are you in California? Because California is 3 hours behind, right? So I was hoping that the California time people will be sort of benefited from this particular lifetime because it won't be actually all that late for them. So Why never sleep is the way to. Reese says call is on fire. Oh, Cali is on fire. California. Literally, Reese. Yes, California does have some fires. Hello, namaste. How are you? Hi, Neeraj. Checking in, Ben. Ben, you're the best. Thank you so much for checking in and letting me know you're here. Much appreciated. Thank you so much. Thank you. We're here. Yay, 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 yay. It's going to snow on Friday. Really? Where? Are you talking about the US? If it snows in Boston, then I better repark my car. Because last time I had to dig it out of the snow, and that was a lot of work. Yes. Okay. Hi, Mac. Oh, yes. It's not late, but still catching up from yesterday. Slept 2 hours. If I don't sleep tonight, I will start hallucinating. Haha. The US. Okay, well, thank you for telling us that it's going to snow on Friday, Harper. And yeah, I do hope that you get more sleep than that crazy sick one. Actually, to be honest, even I did not sleep that well last night. I have been sleeping pretty good. Like I've been getting all my hours of sleep, even though my, schedule is all kind of delayed because of the lives and everything. Sometimes I wake up kind of later, but usually I've been sleeping pretty well, but last night I did not sleep very many hours myself. I just woke up, says Reese. Oh yeah, Reese. You woke up in the middle of the night then. I'm the hallucination. Okay, here's Grimace. All right, now that Grimace is here and Ben has checked in and Doro Doro is also here and Crazy Sick One is insomniac and Reese has woken up, I think we're very much ready for an astronomy live. Pretty much all my physics and astronomy friends are here. If you're joining, this is a cats and books, #cats and books, #physics kind of channel. I will be talking about astronomy primarily tonight. We show kitty cats, we hang out for indefinite hours, and we talk about physics, astronomy, cosmology. Today we're going to talk about the solar system, actually, which I know, pretty crazy for me. The whole gang is in the house. I'll be listening while rocking some games. Let's do this. Hi. Yes, thank you. Yes, please. You kill people in the games. I meant only in video games, only not actual people. And Nausat, and we will be doing this, and you can listen to us. Nausat says, hi, how are you? Thank you. Iggy says, oh, dang. What you playing, Dora? Okay. I want to put something in the chat, too. Hello and enjoy. Okay, so the other day when I believe Reese was the one who asked me about our own sun, I realized that I'm rather ignorant about our own solar system, about our own planet, and other neighboring planets in the solar system, as well as our own sun, which happens to be a rather young star on the main sequence. So we have been talking extensively about the way in which various stars die, because I had been introducing the topic of particle astrophysics, and I remembered, well, one of the big motivations for my own work in particle astrophysics was actually certain very exotic, explosive, very luminous, transient sources such as gamma ray bursts, which is basically part of particle astrophysics in the sense that we might get neutrinos from gamma ray bursts along with other things, such as gamma rays, which is a very small wavelength type of light. In that sort of realm of things, we touched upon the fact that we can also have, of course, various ways in which stars, massive stars, everything from like a low mass star, which would be around a half solar mass, where solar mass is our sun's mass, to everything from, much larger, over 10 solar mass or even more, basically will lead to different types of stellar remnants. So, In that context, we talked about how, depending on the mass, a star, when it dies, will either become a white dwarf or a neutron star or a black hole. And then we covered white dwarfs, what these things are. They are supported by electron degeneracy pressure. We talked about neutron stars, which are not really stars. It's kind of a misnomer. They're not really stars. They're dead stars, but this name has stuck, neutron stars, which are, of course, supported by neutron degeneracy pressure. And then we also talked about black holes. I believe we talked about black holes a couple of lives ago when I was very much awake and not sleepy like the last time I went live, which was last night. So black holes, again, very interesting topic. A lot of people find these to be interesting. And of course, it was one of the first examples of Einstein's equations being solved exactly for something like a black hole. So we have touched upon a black hole in various different contexts when we talked about the 20th century physics and general relativity and Einstein stuff, as well as in the context of astrophysics and how stars die. The most massive stars do become black holes. So we talked about all of this last time. And then I believe I think it was Reese, I'm going to blame him for everything, and I think he will own the questions that he's been asking. That led to basically me having to think about our own sun. And our sun is basically one of those stars which will eventually become a white dwarf. Reese says guilty. Trish says, hi, I'm sorry, I'm at school. Okay. Now Saad says, long time meet you. I will be right back. Thank you. Yes, of course. I'm still here. Class is still not dismissed. We're very much in the middle and just getting started. So, come and join. Thank you so much. Hi, I'm back. Very nice. Welcome. So basically, after kind of having surveyed all these different ways in which stars can die and become either a white dwarf or a neutron star or a black hole, I realized, you know what? Our sun, obviously very young, obviously still on the main sequence, obviously making obviously making helium from hydrogen. Those are basically, there were a bunch of things generally that I do know about our sun, but there's a ton of details that go into where a main sequence star. So first of all, a star has many different phases. We actually touched upon this, where a star will spend a very long time on what we call its main sequence. Once a star gets into its giant phase, where it's truly, the word is giant, where it will become bigger, puff up, it spends less time in its giant phase. It becomes a more inefficient source of power. And pretty much, in short, a star will die if it runs out of its nuclear power. If it basically, it's done burning whatever it is doing to make whatever else. Like, for example, our sun is currently mainly making helium from hydrogen. So the main nuclear physics it's doing is going from taking hydrogen and turning it into helium. If it were to kind of significantly stop doing that, then it's basically getting closer to its death. So ultimately, stars have two main things: nuclear physics going on, as well as its own big gravitation, because a star has a lot of mass. So it can actually collapse under its own gravity, under its own gravitational forces. Basically, all of the mass can just kind of collapse on itself if it does not have another opposing force, which is in this case the nuclear power. So when stars run out of their own nuclear power, which keeps them burning, you will basically get the death of a star, and then you will be left with a stellar remnant after there has been some sort of explosion in the form of like a supernova or something like that, where there might have been a core collapse, basically, and ultimately you get the remnant, which is either a white dwarf or a neutron star or a black hole. But really, there are many, many other steps that are sort of in between, from where the sun was, or from where the star was kind of developing and going through various phases and evolving and aging and going through different phases, to where it will then supernova, core collapse, and turn into a remnant. Lots of different steps. My BFF is going to type here. Hi, Trish. Hello. Welcome to Trish, as well as her BFF and everybody else. Thank you so much for joining. Thank you for being in the live. Thank you for liking the live. Thank you so much. So there are really, really quite a lot of details. And we even looked at a star that is sort of the size of our own sun versus a star that is more like a 5 solar mass type of star. So depending on the mass, so another thing we looked at also is that the mass of the star heavily determines what will be the fate of that star, how it's going to die, how it's going to evolve, how it's going to eventually die, and what type of remnant it will make, which of course are white dwarfs for the lower mass stars, neutron stars for the heavier mass stars, and black holes for the heaviest massive stars. Hi, Berlin. So basically, that's kind of where we were at. So in order to understand more about our own solar system, because we do have a sun and a star, the star in our own solar system is, of course, our sun, just the one. We just have the one sun. So it is rather special to us. In general, I am not a super duper expert on our own solar system, on our own planet, or even our neighboring planets, or our own star, which is the sun. But in this case, I felt, you know what, I should learn a little bit more. So that's what we're going to cover tonight. And basically for this, we're going to reference this book. Hi, Harper. Called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. We have used this book a lot, and I found a very nice chapter on the solar system in this book, so we can talk about this using this book. So here are some basic facts about our own solar system. The sun contains 99.8% of the mass in the solar system. So if you were wondering, as you know that there are, at this point there are 8 planets in our solar system. There's some asteroids, there's some things, but there's some planets. We're on a planet called Earth. We have a bunch of other planets too in the solar system. We used to say that there were 9 planets. Now there's actually 8 because one of them is a dwarf planet. There's some other dwarf planets as well. But the sun, which is the star in this solar system, contains 99.8% of the mass in the solar system. So everybody else is really quite much smaller. What is your favorite planet? I think that is safe to say that my favorite planet is just Earth. The Earth is my favorite. What is your favorite planet? So most of the remaining 0.2% of the mass is confined to a flattened disk. So things get very interesting when we look at things in a little bit more specifics or details. You didn't care about the Earth the other night. Well, I didn't care that the Earth is going to probably go away at some point. Or you asked about the fate of the Earth and the fate of the sun and, the stars die and all that stuff. But in other contexts, I like the Earth. So most of the remaining 0.2% of the mass is confined to a flattened disk. Within this disk, all the planets revolve in the same direction. Most, but not all of the planets rotate in the same direction, and all objects have similar ages, which is 4.6 billion years when measurable. You tell her, Doro. Fight. Yes. So, did you know that all the planets revolve in the same direction? Most, but not all, of the planets rotate in the same direction, and all objects have similar ages, which is around 4.6 billion years when measurable. Ah, she rocks. Just had to say thank you. So we have a plot here. I might show it at some point. We have Mars, Venus, Earth, Mars, all of that in this plot, with the mass going in the y-axis and astronomical units or a distance measure in the x-axis. The 8 largest objects orbiting the sun have been given the collective name planets. The rocky and metallic objects in the asteroid belt, lying primarily between the planets Mars and Jupiter. So some of this might be reviewed to you guys, but did you know that the rocky stuff between Mars and Jupiter are called asteroids? The largest asteroid, Ceres, is also a dwarf planet, according to the definition approved by the International Astronomical Union. Wow, there's a union for this. The icy objects beyond the orbit of Neptune are called trans-Neptunian objects, TNOs. Wow. Many of the known TNOs are in a region just beyond Neptune called the Kuiper Belt. Am I saying that right? Kuiper, Kuiper, The largest known TNOs, Eris, Pluto, Haumea, and Maki are also dwarf planets. So Pluto is now a dwarf planet. I know we grew up, at least I grew up considering Pluto as a planet, but now it's a dwarf planet. Drink water. Well, thank you for the reminder. Pronounced Kuiper. Is it Kuiper? We will Google it. I don't know if okay, maybe it's Kuiper. Okay, thank you. All right, so the planets can be divided into two major types or families, each named after their largest member. The smallest terrestrial planets named after the Earth, alias Terra, terrestrial Terra, are closer to the Sun. The largest Jovian planets named after Jupiter, alias Jovi, are farther from the Sun. Hopefully we kind of knew that. The characteristics, so the thing with what I've realized about the planets in our solar system and just in our solar system is that there are a lot of things that are obvious because we learned it in school, like when we were young, but then there are things that are not as obvious. So I can get tripped up. So we'll see what we learn here today that we didn't know already. It'll be an interesting discussion, and you can always comment too if you know something that we're not covering yet already, or if something is new to you or old to you. The characteristics of the two families are compared and contrasted in a table over here where we see the mass, composition, rotation, satellites, and distance from Sun. So I'll summarize that for you in a bit. Any useful theory for the origin of the solar system must explain the observed differences between terrestrial and Jovian planets. In addition, the following questions should be addressed. Why are planetary orbits nearly circular? So we know that they're elliptical, but why are they, nearly circular? What is the nature and origin of the small debris, such as comets and asteroids? What is the origin of the planetary satellites, such as the moons? Why are there differences in chemical composition among bodies in the solar system? Wow, like pomme de terre, apple of the earth. Oh, really? Potatoes are apple. Oh, yeah, potatoes are apple of the earth. Wow. Pomme de terre, apple of the earth. I didn't know that. Thank you so much. Reese, continue to share more knowledge with us. Thank you. It's French. The dwarf planets Ceres, Pluto, Maki, Haumea, and Eris don't fit into the scheme. Ceres resembles the rocky satellites of the solar system, while Pluto resembles the icy satellites. The properties of Maki, Haumea, and Aries are as yet poorly known, but their high albedo or reflectivity indicates that they have icy surfaces. Bye, Harper. Tuna is chicken of the sea, and alligators are swamp puppies. Oh, goodness. So basically, when we consider stars, often we say their masses in terms of our solar mass, our sun's mass, right? When we say one solar mass, it's one sun mass. In terms of planets, we often Hi, Stephen. Hi, Stephen, you're back. Yay. We often compare to the Earth mass, so one Earth mass, right? So terrestrial planets, that is the ones that are the ones that are smaller, basically, have low mass. They're less than the mass of the Earth. Jovian planets are greater than 10 Earth masses. Composition of the terrestrial planets are rocky or metallic. Composition of the Jovian planets are gaseous or icy. The rotation of terrestrial planets is considered slow, where the period is greater than or equal to 24 hours. So our 24 hours, it's even, might be the rotation is slower for the other terrestrial planets. For Jovian, it is fast. The period is less than 18 hours. Satellites, terrestrial planets have a few. Satellites of Jovian planets, they have many. Distance from the sun is less than 2 astronomical units for the terrestrial planets and greater than 5 astronomical units for the Jovian planets. Steven says, I'm watching you on my TV and chatting tonight. Oh, nice. Thank you so much. Thank you for watching me on your TV. Why are there rings around the Jovian planets and not around the terrestrial planets? So that's another question. So this is what I meant. When I was reviewing this, I was like, you know what? There are things that people, kids are taught about the solar system, about our planets, about the, about our neighboring surroundings, basically, in this galaxy. But there's always more details that are left out in school and we might not know. For example, why are there rings around the Jovian planets and not around the terrestrial planets? Why are the terrestrial planets chemically differentiated with a rocky outer layer wrapped around a metallic core? We will first describe the physical characteristics of the constituents of the solar system, introducing new physical concepts as necessary. We will then try to put these elements into a single coherent picture of the solar system. Yay! So that's what we're going to do. My favorite planet will always be Pluto, and Saturn was so happy when New Horizon visited Pluto. So you mean the dwarf planet Pluto and the regular planet Saturn. What is your favorite planet? Pin message. Pluto will always be a planet. Yeah. Some people are willing to die on the Pluto as a dwarf planet hill. And what can I say? At this point, it's whatever for me. I really don't care enough about planets in general to, that. But yeah, my favorite planet, just to keep it simple, is Earth. This is an anti-Earth stream. Oh, come on. Pluto gang. There you go. The masses of astronomical objects are measured by looking at how they accelerate neighboring objects. It is particularly easy to measure the mass of a planet when it has a nearby small satellite. In that case, it is a simple matter of applying Kepler's third law. So that's so interesting. If somebody has a moon, yeah, me too. I mean, I grew up with Pluto being a planet. I get it. So basically, planets that if you have a moon and if you see sort of its behavior with Kepler's third law, you can actually figure out the mass of the planet. Isn't that cool? Isn't that so nice? That math and physics helps you to determine things with this is classical physics. So amazing. There you go. Planets that do not have satellites, that is Mercury and Venus, pose a more difficult problem. So basically, if somebody has a moon, such as a planet with a moon or many moons, looking at the moons, we can basically figure out the mass of that planet by doing Kepler's third law. I want a cup of tea, but I'm ill. Carry me someone. Oh no. Hopefully you can make this cup of tea or somebody can help you. Gonna drag myself down. I do love our home world, but I will admit I love Io and Titan as moons. Yeah, that's okay. Actually, next I'm gonna ask you about moons. What is your favorite moon? So, so there are some things about that. Now, before the advent of interplanetary space probes, the masses of Venus and Mercury were determined from their tiny perturbations to the orbits of other planets. Wow. Much more accurate masses are now available from space probes that have flown by them or orbited them. The radius r of a planet is computed from its measured angular radius and its distance. The mean density can then be computed from the known radius and mass, which is rho is equal to 3m over 4 pi r cubed. Densities of rho getting around 700, which is 2,000 kilometers per meter cubed, are typical of Jovian planets, indicating a composition that is mostly gas or ice, where ice in the language of astronomers can refer to frozen water, but also to frozen carbon dioxide or dry ice, frozen methane, and frozen ammonia. So what we mean by this mostly gas or ice Jovian planets is the ice can be frozen water, frozen carbon dioxide, frozen methane, frozen ammonia. The lowest density Jovian planet, Saturn, has a mean density of 710 kilograms per meter cubed, which is less than that of water. Densities of rho going from 3,000 to 5,500 kilograms per meter cubed are typical of terrestrial planets, indicating a composition that is mostly rock and metal. Look at that. From all these densities, they know. I grew up with the Apollo moon landings. Oh, wow. Look at that. From these densities, they can figure out the composition. The surface temperature T of objects in the solar system depends on a number of factors. Since the sun is an important source of energy, the temperature of an object depends on its distance from the sun and on its albedo or reflectivity. However, the surface temperature also depends on whether the object has any internal heat sources and whether it has an atmosphere that can act as an insulating blanket wrapped around its surface. So many things. The sun, to a rough approximation, radiates like a black body, so we can do math with the sun's luminosity. Ooh. So they have done some math of the equilibrium black body temperature for a spherical black body of uniform temperature at a distance r from the sun, Earth and our moon. I grew up with the Apollo moon landings, Earth and our moon. I'm dubious about the moon landings. If I can put my... What? Hi, God is the best, so is family. Reese, are you saying that we did not land on the moon? So, basically, there's some... You know what? We're going to read about this. So there's some mathematics I don't think we did. Are you serious? Why? Why do you think we did not land on the moon? So, okay, so after the black body math, we'll keep going. For purposes, okay. The Earth and Neptune are rapid rotators, and although Venus is a slow rotator, it has a dense atmosphere with global mixing. We see, however, that all the planets are warmer than expected. Neptune is warmer than expected because, like all the Jovian planets, it started its existence much hotter than it is today and has not had time to radiate away all its internal heat. Both the Earth and Venus are warmer than expected because of the greenhouse effect. So this greenhouse effect, because of having an atmosphere, can make the planet warmer. Ooh, so look at this. Venus has... Oh, look at that. Venus has a temperature of... What is TBB? T black body. Got it. TSS. Subsolar black body temperature. I will admit I do believe we landed on the moon. Me too. I believe we did land on the moon. Anyway, moving on. The greenhouse effect occurs when a planet's atmosphere is transparent at visible wavelengths but opaque at infrared wavelengths. Oh my gosh. This is so cool. we're going to learn about greenhouse effects. So because we have an atmosphere, listen up. The greenhouse effect occurs when a planet's atmosphere is transparent at visible wavelengths, but opaque at infrared wavelengths. To see why that influences temperature at the planet's surface, consider the energy radiated by the warm surface. For the Earth, with Tp around 290 Kelvin, the Planck spectrum peaks at lambda p wavelength of around 10 microns. For Venus, with Tp around 740 kelvins, so a lot higher than Earth, the peak is 4 microns. These wavelengths are in the infrared range of the spectrum. If the atmosphere is opaque at infrared wavelengths, the radiated light will not freely escape from the atmosphere. Instead, it will be absorbed and re-radiated until the light energy makes its way to the upper atmosphere. Isn't that cool? Where the optical depth at infrared wavelengths drops to around tau of 1. Then, at last, the light can escape. Thus, the photosphere of the Earth and Venus, the layer from which their radiated infrared light escapes, is higher than and cooler than the solid surface of the planet. Naturally occurring greenhouse gases, including water vapor, H2O, carbon dioxide, CO2, and methane, CH4. The greenhouse effect is particularly strong on Venus because its dense atmosphere is roughly 95% carbon dioxide. Oh my gosh. The flux of light we observe from a planet depends on wavelength. Consider as an example the planet Neptune. With a measured temperature of T of 59 kelvins, so that's very low, using Wien's law, its spectrum should peak at a wavelength of around 50 microns. In the far infrared, the light we see from Neptune at visible wavelengths is reflected sunlight modified by absorption in the atmosphere of Neptune. Uranus and Neptune both appear bluer than the Sun at visible wavelengths because their atmospheres contain methane, which strongly absorbs red wavelengths of light. The spectrum of a planet can thus be roughly approximated as the sum of two black-body spectra. One spectrum is that of reflected sunlight, containing both the Fraunhofer absorption lines of sunlight and any absorption lines contributed by the planet itself. The other spectrum is that of planet's thermal emission. The reflected sunlight has an integrated energy proportional to the albedo A, which is reflectivity. The thermal emission has an energy proportional to 1 minus A, plus any internal source of energy. For instance, iron oxide in the soil of Mars strongly absorbs blue light and thus makes Mars appear reddish at visible wavelengths. So Mars does appear reddish, that's true. And there's also a lot of iron oxide in Mars. Mars looks red because it's rusty. Mars is rusty. Rusty Mars. The thermal emission peaks at 13 microns, corresponding to a temperature of around 225 Kelvin, which is around minus 48 degrees Celsius, above average for Mars. So it's kind of cold in Mars. Everybody who wants to go to Mars, it's kind of cold there. Who all believe in the moon landing? Yes. Please write in the chat if you believe in the moon landing or not. I did not think that was a debate, but sure. An underlying reason for many of the observed differences between terrestrial and Jovian planets is that the Jovian planets have a chemical composition that closely resembles that of the Sun. That is, they are mostly, so look at this. An underlying reason for many of the observed differences between terrestrial and Jovian planets is that the Jovian planets have a chemical composition that closely resembles that of the sun. That is, they're mostly hydrogen and helium, which is what the sun is doing. The terrestrial planets are deficient in hydrogen and helium because they're too hot to retain such light elements. Let's consider the conditions under which planets can retain different atmospheric gases. The hotter a planet's atmosphere, the higher the random thermal speeds of the individual gas particles. In a dense atmosphere, though, any individual particle will travel only a short distance before colliding with another particle and changing its velocity. In the Earth's atmosphere at sea level, for instance, we computed the mean free path of a typical molecule to be only around 400 angstroms. Angstrom is 10 to the minus 10 meters, okay? However, at higher levels in the atmosphere, the density of molecules decreases and the mean free path therefore increases. At some height in the atmosphere, the mean free path increases to the point where a gas particle moving upward faster than the escape speed is able to escape from the atmosphere before colliding with another particle. This height is called the exobase, and the layer of the atmosphere above the exobase is called the exosphere. Oh my gosh. So now there's some gas math, which basically says that the Earth's exobase has a higher temperature than the atmosphere at sea level because the upper atmosphere is heated by interactions with high-energy solar wind particles during daytime. The exobase temperature is around 1,000 kelvins. Scaling to the temperature of the Earth's exobase, we find that the condition for retaining a gas is, there's some equations for conditions of retaining a gas. That's the Earth where Rx is 1.08 can retain gases. So basically, this is all about can we retain gases or not. That Mercury would be able to retain only highly massive molecules in its atmosphere. So during daytime on Mercury, the retention condition for gas particles is 34, where I think that 34 is the number given to highly massive. Love your streams, but we definitely never landed on the moon. Everyone is coming out to argue the moon landing. Yes, they are arguing the moon landing. Not something that I thought we would be doing. Somehow, Reese, is this you again? You did this, didn't you? Reese is the one who said that he does not believe in the moon landing. And now there are other people too who all believe in the face of Mars. How about Uranus? I'm with Elon Musk. I want to land on Mars. No, we never landed on the moon. We will land on Mars one day, I'd say in the next 10 to 20 years, and we landed on the moon, says Steven. Moon landing deniers are winning. Are you serious right now? What have you done? What have you done, Reese? Okay, so we skipped over some math, but basically there's some math for which molecules will be retained by a planet depending on temperature and gas and all that. We will get to another part now. Formation of the solar system. We will talk about formation of the solar system. Harper, that's okay. Let's forget about the moon landing, but one last thing, we did land on the moon. Done. So now we will give a broad overview of current ideas about how the solar system formed. The modern view of planetary formation is that it is a natural consequence of star formation. Put simply, formation of planets is a way for a collapsing gas cloud to rid itself of angular momentum so that it can shrink to the size of a star. So when there's a collapsing gas cloud, we may just see a star and some planets. So formation of planets is a way for a collapsing gas cloud to rid itself of angular momentum so that it can shrink to the size of a star. Star formation occurs when a large gas cloud collapses under its own gravity. Since this can happen only if the self-gravity exceeds the support provided by gas pressure, star formation occurs only in dense, cold, and by cold we mean T less than equal to 10 kelvins, regions of interstellar gas. So you need a collapsing gas cloud, but remember, gas also has gas pressure. So you can't, gas wants to do the thing where it goes out, right? And kind of disperses, diffuses. We were just talking about how some molecules, depending on their mass, etc., could be, doing things in a gas way or whatever. There's some math for that. Well, let's think about the gas cloud from which we came. Our Earth came, our planets came, and the sun came. So, star formation occurs when a large gas cloud collapses under its own gravity. Since this can happen only if the self-gravity exceeds the support provided by gas pressure, star formation occurs only in dense, cold regions of interstellar gas. If the collapsing gas cloud has a net angular momentum, it will collapse until it forms a rotationally supported disk. The dense central region of the disk ultimately becomes a star, while smaller condensations that occur within the disk ultimately grow into planets. So we are just itty-bitty little condensations of this gas cloud. And the dense central region of the disk of the gas cloud condensation becomes a star, while smaller condensations that occur within the disk ultimately grow into planets. Such rotationally supported dusty gaseous disks called protoplanetary disks are seen around young stars in our galaxy. There's an image of a protoplanetary disk right here, actually. I'll take a look at that. See that thing with the two shiny things and the thing in the middle? Such rotationally supported dusty gaseous disks called protoplanetary disks are seen around young stars in our galaxy. This picture I just showed you shows a protoplanetary disk in the Orion Nebula. The edge-on protoplanetary disk resembles an edge-on hamburger. The dark patty represents a thin, dust-rich disk, and the bright buns, so like the bright parts on the top and bottom, consist of light from the central protostar, scattered by a more diffuse distribution of dust. The first step in planet formation is condensation, the formation of solid particles within the gaseous disk as it cools. Different materials condense into solids at different temperatures. Metals condense at high temperatures. Rocky materials at intermediate temperatures, and ices at low temperatures. So that's the other thing. There is condensation, but depending on the type of stuff that's condensing, I guess, you're going to have condensation. So different materials condense into solids at different temperatures. Metals condense at high temperatures, rocky materials at intermediate temperatures, and ices at low temperatures. Materials that condense into a solid or liquid only at a very low temperature are called volatile materials. The gaseous disk from which the planets ultimately form is hottest at the center, where the proto-sun is located, and becomes cooler with increasing distance. So we were we were close to that proto-sun, to the baby sun, when the sun was being formed as well from this gas cloud. So because we're close to the baby sun, the gaseous disk from which the planets ultimately form is hottest at the center where the protosun is located and becomes cooler with increasing distance. In the central parts of the protoplanetary disk, only the most refractory materials can condense to form solid particles. A refractory material is one that condenses into a solid or liquid at relatively high temperatures. In the outer parts of the disk, by contrast, the temperature is sufficiently low that even volatile materials can condense. Oh, we have a table of different things that can condensate at different temperatures. So we have metal oxides can condensate at 1500 kelvins. For example, in mercury, we have iron nickel condensating at 1300 kelvins, silicates at 1200 kelvins, iron sulfide at 700 kelvins. For example, in Venus, H2O or water, which can condensate at 200 kelvins, for example, on Earth and Mars. NH3 ammonia at 150 kelvins on the Jovian planets. CH4 methane at 120 kelvins, for example, on Pluto and Eris. And then argon and neon can condensate at 65 kelvins. Wow. Look at this. Look at this. Hi, we did not land on the moon. How are you? Condensation, more specifically, is the process by which solids grow molecule by molecule, as individual molecules or atoms adhere to the solid body. Hi, Stephen. As an example, snowflakes grow by condensation. Eventually, when are we going back to the moon? As in, when are we going to land on the moon again? Condensation. So now we know different materials condensate at different temperatures, all the way from metal oxides condensating at 1500 kelvins in something like mercury, to iron sulfides condensating at 700 kelvins in something like Venus, to water, for example, on Earth and Mars, condensating at something like 200 kelvins. I guess Americans did. Yes, we did land on the moon. Condensation, more specifically, is the process by which solids grow molecule by molecule. So this is now explaining what condensation is. So solids grow molecule by molecule as individual molecules or atoms adhere to the solid body. As an example, snowflakes grow by condensation. So even snowflakes are a type of condensation. Eventually, however, the major mode of growth switches over from condensation to accretion, in which solid condensates come together and are held together by weak electrical forces. For instance, individual snowflakes can accrete together to form a snowball. Did anyone make a snowball during the snows this winter? In the early solar system, the collisions between individual condensates or snowflakes are gentle. Aww, since they are on similar orbits. Objects grow by accretion until they are roughly 1 kilometer across. These intermediate-sized bodies are called planetesimals. Planetesimals, or baby planets. Near the sun, planetesimals are made of the least volatile materials, metal oxides and metals. Farther from the sun, where the temperatures are cooler, the planetesimals are made of a mix of materials with different degrees of volatility. Eventually, planetesimals are drawn toward each other by gravity and merge to form larger bodies. This process is known as coalescence. Coalescence. Since only the least volatile materials can condense close to the sun, the planets built up the coalescence within 1.5 astronomical units of the sun are rich in low volatility elements, such as us on Earth, even though such elements are relatively rare in the universe at large. These metal-rich and silicate-rich bodies close to the sun are the terrestrial planets. Yay! So once again, eventually planetesimals are drawn toward each other by gravity and merge to form larger bodies. This process is known as coalescence. Since only the least volatile materials can condense close to the sun, because their condensation temperature is higher, right? The planets built up by the coalescence within 1.5 astronomical units of the sun, as in a close distance to the sun, are rich in low volatility elements, even though such elements are relatively rare in the universe at large. For example, what the Earth is mainly made of is not something that is super abundant in the universe at large. Again, quiz question, what is the most abundant element of the universe? I know we talked about this earlier, so yes, you guys know that. Hydrogen in the universe. Silica on Earth, but yes, hydrogen is the most abundant element in the universe. And we already talked sort of about how the universe formed from start to the present in one of my cosmology lives, but we can certainly do that again. Yes, indeed. We did land on the moon. We do have lots of hydrogen, though, in the universe at large. Yes. So we have talked about the evolution of the universe, the start of the universe and all that stuff. Early universe, Big Bang, nucleosynthesis. So actually, Reese, if you are looking at my live streams from a while ago, I think something called Big Bang, nucleosynthesis, and around there, we talked about the universe from start to the current moment. But certainly we will talk about it again. I will sub. I'm clearly needed here. Yes, for sure. Please do subscribe. Thank you. Yeah, no worries. Yeah, okay, thanks. Yes, for sure. And we will definitely talk about the universe more. You know, we will go back to more of a cosmology topic for sure. It's definitely very interesting. We will definitely talk about the evolution of the universe more. Thank you. Like the stream, please, guys. Thank you. So these metal-rich and silicate-rich bodies close to the sun are the terrestrial planets. So remember, being metal-rich and being silicate-rich is pretty rare overall in the universe. For example, in the universe, mostly what we have is hydrogen, which is the number one most abundant element in the universe. It's what the Big Bang pretty much made. And as you can see, later on, stars and stuff are later on story in the universe, and you need stars to make the heavier elements, heavier than helium. And even helium is made, mostly in stars. So basically, this whole being metal rich and silicate rich is kind of special. So we should be thankful we have this on Earth. Earth is very special in that sense. So these metal rich and silicate rich bodies close to the sun are the terrestrial planets. Since materials with low volatility tend to be dense, the terrestrial planets all have high densities. So let me tell you about some of our densities. So Mercury's density is 5,400 kilograms per meter cubed. Venus's density is 4,200 kilograms per meter cubed. Earth is also 4,200 kilograms per meter cubed, and Mars is 3,300 kilograms per meter cubed. So Mars is less dense than Venus and Earth. So I think I mentioned earlier at one point that Venus is a lot like Earth actually in size and apparently the density. So if I had to pick another planet to go to, it would be Venus, but unfortunately I believe its atmosphere is rather poisonous. Stinky. Yes. Okay. So this is where I listed off the uncompressed densities of the terrestrial planets. In other words, this is the density of the planet would have if it were not squeezed to a smaller volume and higher density by its own gravity. So these are the uncompressed densities of terrestrial planets that I listed off, as in when they're not squeezed further under its own gravity, that would be the density. Note that the uncompressed density of the terrestrial planets decreases. So note that it decreases with increasing distance from the sun. Mercury had the highest density and Mars had the lowest. It is interesting, however, that the uncompressed density of the moon, our moon, is only 3,350 kilograms per meter cubed, much less than the Earth's uncompressed density, despite the fact that they're at the same distance from the sun. The unexpectedly low density of the moon is a consequence of its unique formation history, which we'll talk about later. In the outer part of the protoplanetary disk containing planetesimals of both high volatility and low volatility materials, larger bodies are able to form. Once these protoplanets reach a mass of around 15 Earth masses, they're massive enough, given the low temperatures in the outer disk, to retain hydrogen and helium. So they're massive enough to retain hydrogen and helium, massive enough given that the temperatures are lower out there. They're massive enough to retain hydrogen and helium. Since hydrogen and helium are the most abundant elements, being able to hang on to them permits the Jovian planets to grow to much larger masses than the terrestrial planets. Protoplanets grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. So they grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. During and immediately following this early phase of coalescence, the interior and surface structure of terrestrial planets are changed by several processes, among them chemical differentiation, cratering, volcanic flooding, and slower processes of surface evolution. Chemical differentiation is the process by which dense elements sink to the center of terrestrial planets. So how cool is this? So by the way, another reason why I don't know much about the Earth is because that's geophysics. And I did not do geophysics. So studying the Earth, etc., that's a whole nother field. We will learn about it a little bit here today, but this is really a much larger field. Okay, so protoplanets grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. And then there's pretty much after the protoplanets are formed from the coalescence, there's a bunch of interior and surface structure of terrestrial planets. There are a bunch of processes by which the interior and the surface structure of terrestrial planets are changed. And these are chemical differentiation, cratering, volcanic flooding, and slower processes of surface evolution. So chemical differentiation is the process by which dense elements sink to the center of terrestrial planets while the lower density elements float up to the surface. Since planets form by a jumbled coalescence of planetesimals of differing chemical composition, we might expect that planets would show the same jumble at their center as at their surface. However, study of the interiors of terrestrial planets show that they are chemically differentiated. That is, their chemical composition varies with distance from the center. the cores of terrestrial planets are rich in dense elements like iron and nickel, with uncompressed densities of 8,000 to 9,000 kilograms per meter cubed. However, their outer layers are primarily made of silicate rocks. We know that. Our beaches are made of silica, sand, with typical uncompressed densities of around 3,000 kilograms per meter cubed. Differentiation occurs naturally in a fluid body. So we're a fluid body. Wow. The denser material sinks while the lower density material rises to the top. The fact that terrestrial planets are differentiated is an indication that they were once hot enough to be fully molten. So this differentiation happened where the dense stuff actually sank to the center. Wow. The dense stuff actually sank to the center of these terrestrial planets. So everything was molten enough to where the dense stuff was able to sink and the lighter stuff floated up to the top. So we have sandy beaches instead of iron and nickel beaches. So the cores of terrestrial planets are rich in dense elements like iron and nickel with uncompressed densities going from 8,000 to 9,000 kilograms per meter cubed. However, their outer layers are primarily made of silicate rocks with typical uncompressed densities of 3,000 kilograms per meter cubed. Wow. And pretty much the moon is that same density, but its overall density is lower. Okay. Differentiation occurs naturally in a fluid body. The denser material sinks while the lower density material rises to the top. The fact that terrestrial planets are differentiated is an indication that they were once hot enough to be fully molten. In the Earth, the radioactive decay of elements such as uranium, thorium, and potassium-40 releases enough heat to melt iron. The iron, as it sinks toward the Earth's center, converts a gravitational potential energy into heat, leading to an iron catastrophe that is a runaway heating process that does not cease until the interior is highly differentiated. Wow. So basically, the radioactive decay of elements such as uranium, thorium, and potassium-40 releases enough heat to melt iron. Wow. The iron, as it sinks toward the Earth's center, converts gravitational potential energy as it's sinking, because if you're over here, you have a gravitational potential energy of mgh, right? Where h is the height from the Earth's surface. So if you sink, you release gravitational potential energy, convert that into heat, leading to an iron catastrophe that is a runaway heating process that doesn't cease until the interior is highly differentiated. So basically the interior is molten, so the heaviest stuff will sink to the center and the lighter stuff will sink up. So pretty much that process of differentiation is more and more as things are more and more molten, which the Earth's center is very molten. Cratering. So this is another thing, cratering. Cratering begins as the newly formed planets sweep up the remaining planetesimals. Fermi paradox? I know Fermi. Remind me what the Fermi paradox is again. So that was the chemical differentiation process. Yeah, it is called chemical differentiation. So what I just talked about, the iron and nickel going to the center, and the center being molten because of so much heat from the radioactive stuff, etc., and that leading to even more differentiation within the Earth's molten center. That's called chemical differentiation in the Earth, or in other planets too. Cratering. So now we know that the moon has craters, all those imperfections on the moon, right? It's basically him asking the question, where is the alien life in the universe, and questioning the lack of it. So cratering begins as the newly formed planets sweep up the remaining planetesimals. So as this, remember, the coalescent stuff happens, planetesimals form. Basically, you can kind of continue to sweep up the remaining planetesimals as you're coalescing. The process of cratering modifies the outer crust of the terrestrial planets. For instance, cratering has given Mercury its characteristically pockmarked appearance. Cratering was an important process until about 3.3 billion years ago. At that time, the early period of heavy bombardment ended because the planetesimals and other small objects had been largely cleared out of the inner solar system. So apparently, cratering is when you pick up upon, you basically pick up. Hi, James. Hello. Hello. Hi, aliens. So I guess the period of heavy bombardment ended about 3.3 billion years ago. And pretty much at that point, the small objects had been kind of swept up by these coalescing planets. Volcanic flooding of planetary surfaces. So this is another process. Volcanic flooding of planetary surfaces occurred at the same time as cratering. Fracturing a planet's crust by large impacts leads to flooding of the surface by lava welling up from below. So basically, at the same time as cratering, if you fracture a planet's crust, oh, thank you. For the past 30 odd minutes, I've been watching some. Thank you so much for watching. Thank you for being here. Welcome. So, at the same time as cratering, if you fracture a planet's crust by large impacts, then it leads to flooding of the surface by lava welling up from below. This obliterates the old surface features. Craters are paved over by lava, just as old potholes in a road are paved over by a new layer of asphalt. Surface features on a terrestrial planet can also be worn away by slower processes such as erosion by wind and water. Guess what? Name something in America that was very much eroded by wind and water. I will leave that question to Stephen. At the same time, surface features can be built up by other slow processes such as plate tectonics and volcanism. On a geologically active body, such as the Earth, surface features are in a constant state of flux. So Earth is very much a geologically active body. Of course, geophysics people will know more about that. But we do know of certain surface features that are very much made by erosion by wind and water. And quiz question for the populace here. Tell us some examples of what you know about that. And Stephen will cover the main one from North America. The surface of a terrestrial planet can change with time, so can its atmosphere. The primeval atmosphere of a planet is whatever is left behind by the formation process. So that's the initial atmosphere. The atmospheres of terrestrial planets evolve for several reasons. Outgassing from the planet's interior releases gases that were trapped in the interior during the formation process. So, in the beginning, whatever atmosphere we get is whatever atmosphere, was left behind by the formation process. But over time, even the atmosphere can change due to something like outgassing from the planet's interior releases gases that were trapped in the interior during the formation process. These planetary, let's see what Stephen has to say about what famous structures do we know that are results from erosion with water and wind in North America, especially. These planetary belches, so the planet can belch, Earth can belch, have a little bit of a belch. These planetary belches occur as part of the differentiation process and continue through ongoing volcanic activity. Yes, that's what I had in mind. I had the canyons in mind. We have some pretty big, pretty breathtaking canyons in North America. I've only been just up. Oh wow, James. Okay. Right. That's right. You've pressed the like button. Thank you. Thank you so much. Can we get 20 likes, please? I think I see 19 likes. That would be nice if we got an even 20. The Blue Ridge Mountains, mountain range that predates the Rockies, Grand Canyon. Yes! I basically had in mind the Grand Canyon or even something like the Antelope Canyon. You know what I mean? Like North America has such amazing canyons. Devil's Tower is another good example of erosion too. Thank you, Stephen. What is Devil's Tower? Where is that, Stephen? Glad you're back, James. You had me laughing hard last time. Yeah, James is back. The thong guy, or sorry, did I say that right? I forget. I forget what. James and his clothes. That's right. Biden's face is also great. Reese, you are already in a lot of trouble. If you cause any more chaos today, Mr. Belgium, that's it for you. I'm bringing down the hammer. You know, whoever I make the mod on this channel usually is the one who just, what's the phrase? Flies off the handle. Like they are the ones causing the most chaos in the stream. Seriously, what you think of me wearing my mother's red rose lace with the matching and relaxing? Well, James, you should wear whatever you want. I think at South Dakota, it's the ancient remains of an extinct Really? Stephen, tell me more. So Stephen, by the way, I am learning more and more about the United States. I still have 17 more states to visit. And actually, South Dakota is one of the states that I have left. Doro, well, make me mod next. I'll go wild after a few streams. I will. You both can be mod. You both can be mod. Here, Doro Madness is a mod too. Let's just see now what Doro does. Doro can be mod too. Reese is a mod who has caused a bunch of chaos, and now Doro we will see. I'll go listening. Thank you. Okay, so one way in which our atmosphere can change is actually by the Earth letting out some belches from its belly. So interior releases of the gas that were trapped in the interior during the formation process. So remember, the planet during formation process could have some gas trapped within the belly of the planet, and these planetary belches occur as part of the differentiation process and continue through ongoing volcanic activity, because it's an ongoing differentiation process where the lighter stuff will come up and the heavier stuff will sink. Okay? Chemical interactions between the atmosphere and the surface can alter the atmosphere's composition as well. For instance, the interaction of gaseous carbon dioxide with liquid water removed most of the carbon dioxide from the Earth's atmosphere and dissolved it in the Earth's ocean. James is not trolling. Doro is now a mod as well. We've added Doro as a mod. I'll have to keep my cool. I like the stream. Been here too long. We might be mods, but we love banter. In the movie, you see Devil's Tower at the end of the movie. Oh, which movie? I don't think I... Oh, Close Encounters of the Third Kind. I see. Okay. So yeah, South Dakota is part of my list. The North America, you know, the United States has a ton of very interesting such things that we're talking about right now. Earth features, right? So James is hilarious. Sure, James, you're dead serious. He has changed into his mother's black silk. Very nice. South Dakota is awesome. Travel for work all the time. Cool place. The two best alien movies. So, really, is South Dakota awesome? Can you say some more things about South Dakota? I actually am missing that. South Dakota, North Dakota, I think Montana. I've been to Utah. I did Utah, Arizona, Nevada, you know, as part of my Las Vegas visit. And then I did toured, or what do you call, guided tours of all the different canyons and dams and things like that. Ooh, also Wyoming I'm missing. Sorry, Wyoming is where Devil's Tower is located. I had to look it up. Okay, good. Good to know. Yeah, I'm missing Wyoming, North Dakota, South Dakota, Montana, Oregon, New Mexico. Yeah, there's like 17 states that I'm missing at this point. I'm trying to cover all the states in the US. Most of the time for work was in Pierre, the capital. Spent most of it downtown. Pierre, okay? But got out a little bit and saw a bunch of suburbs, very homey feeling to it. It was one of the best alien movies I love to watch. Is that the mashed potato tower, Stephen? Oh, Reese. Okay. Chemical interactions between the atmosphere and the surface can alter the atmosphere's composition. For instance, the interaction of gaseous carbon dioxide with liquid water removed. So the interaction between gaseous carbon dioxide and liquid water removed most of the carbon dioxide from the Earth's atmosphere and dissolved it in the Earth's oceans. The mechanism by which planetary magnetic fields are generated is poorly understood. In general terms, it's their food. In general terms, it is thought to result from dynamo action in the planetary core. Hot, partially ionized matter wells up by convection in planetary interiors and is deflected by the Coriolis effect. Our expectation then is that the larger magnetic fields will be found to be associated with larger bodies, which will have larger liquid cores, and faster rotators, which will have a larger Coriolis effect. In fact, as we will see, the planet Jupiter, which is both the largest and the fastest rotating planet in the solar system, has the strongest magnetic field. So how exactly we have planetary magnetic fields is something that we don't fully understand, but we will continue to look at going forward. But some of the guesses are that it might have to do with the Coriolis effect, because Jupiter, which is both the largest and the fastest rotating planet in the solar system, has the strongest magnetic field, turns out. So interesting things like that. Now, basically we covered, that was the overview of the solar system. Good night, James. Have a good day at work. Black silk, okay. Has anybody seen the pentagon-shaped cloud formation in the North Polar region of Saturn? Okay, so now let's talk about a little bit more about the Earth and the Moon. Next, okay? We will talk a little bit more about the Earth and the Moon. Pretty fascinating, yeah. So, right, so we just saw that the Moon's uncompressed density is lower than the Earth's uncompressed density. And so we will look into a little bit about that. And by the way, there was a footnote that we missed earlier. The Earth is the most massive terrestrial planet, by the way. I hope you knew that already, might have known that already. The Earth is the most massive terrestrial planet and has the greatest gravitational compression. The measured mean density of the Earth is around 5,500 kilograms per meter cubed, significantly higher than its uncompressed density of 4,200 kilograms per meter cubed. So if there was no compression due to gravity, Earth would have the same density as Venus, and Mercury has, remember, uncompressed density of 5,400, Venus and Earth 4,200, and Mars is 3,300. And we saw that the Moon was around 3,300 as well. And we will see why, because the Moon and the Earth are at the same distance away from the Sun, and the Earth is the most massive terrestrial planet. And the measured mean density of the Earth, again, is 5,500 kilograms per meter cubed, which is significantly higher than its uncompressed density of 4,200 kilograms per meter cubed. So those are some more facts. And then now we will go over to learning about the Earth and the Moon. I think it's kind of fascinating, actually, to talk about the Moon, so we will. Yay! Our moon, right? Our sun, our moon, our solar system. Okay. 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 So I actually like the moon more than the Earth, I think. So somebody was saying that I don't care about the Earth. It's true. I mean, I care about it, but there's different levels of caring, right? I think I actually like the moon more. I love the moon. I love looking at the moon. I mean, it's there, you know. I've always had a poetic relationship with the moon. The moon has always been there for me. So yeah, ever since I was a child, I've kind of liked the moon, actually. The lunar maria are seen as darker, smoother regions on the moon's surface. Did you know? Lunar maria. The moon is always cool. Yeah. Okay, so let's read about the moon a little bit. Let me drink some water and then we will. How are you guys? Actually, it's kind of cold. I'm gonna turn off the heat. Hi, Flowey. Hi, Fuji baby. Oh gosh, it's so cold. It's so cold. The Earth's moon. This sweater, by the way, was made by my grandmother. Yay, grandma fashion. The Earth's moon has an average density of rho equal to 3370 kilograms per meter cubed. There is a theory that the moon was actually two moons. Okay. About the same as the density of the Earth's crust. Because of the moon's small size, it has cooled more rapidly than the Earth, leaving it nearly dead, geologically speaking. Because geologically active, when things are still kind of happening, you have like molten insides. Grandma fashion? Yes, my grandma made this sweater. I think it might have even been my brother's sweater. I inherited a lot of my brother's clothes, and his like boy clothes still kind of fit me, so here we are. So my grandmother probably made sweaters for both me and my brother, but most of them ended up with me because I fit in them, and he... That's not something you hear from girls often. It's a nice sweater. Right? Isn't it so nice? She made it. And she's not there anymore, so I have her stuff, the sweaters she made by hand. Hi, Baji. Not something you hear from girls. Well, it helps that I look good in almost anything. Look, the back is red and the front is dark. Oh my God. She's rocking a boy sweater and James is rocking mom clothes. James and his mom clothes. Good job. Thank you, 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 thank you. What? You don't believe James? I think he really wants you to believe him. Believe him and then release him. I don't think he's appreciating that you don't believe him. Because of the moon's small size, it has cooled more rapidly than the Earth, leaving it nearly dead, geologically speaking. Moonquakes are rare and weak. So by the way, if we lived on the moon, we would not have too many moonquakes. Our man James is trolling. I have to wake up at 5. Hi, Harper. I thought you were already in bed. So moonquakes are pretty rare and weak because because the moon is pretty much, geologically speaking, kind of dead. However, seismic instruments left at the Apollo landing sites, by the way, those people who did not believe in the moon landing, here we are. Stephen, I know you said goodnight, but you might want to stay for this part because we're going to talk about the Apollo landing sites. Moonquakes are rare and weak. However, seismic instruments left at the Apollo landing sites were able to record artificial moonquakes generated by discarded Apollo ascent stages and Saturn V third stages crashing onto the surface, and by explosive charges set by astronauts. They were able to do artificial moonquakes. From the analysis of the seismological data, it is known that the moon has a solid core of density around 3,500 kilograms per meter cubed. So seismic, not seismic. You're pronounced as a seismic. I'm still going to say seismic because that's too hard. So they did all these explosive stuff. Her accent may dictate otherwise. I always like to learn more words, but right now I'm thinking about these explosions. So they did these explosive charges set by the astronauts. So they did all this to figure out the density of the moon when they landed on the moon. Seismic is the correct spelling. Yes. Seismic. S-E. I know there's an E there. Seismic. You might be right. Maybe it is seismic. However, seismic, it feels weird now to say it that way. Seismic instruments left at the Apollo landing sites were able to record artificial moonquakes generated by discarded Apollo ascent stages and Saturn V or 5 third stages crashing onto the surface and by explosive charges set by astronauts. From the analysis of the seismological data, it is known that the moon has a solid core of density around 3,500. 3,500 kilograms per meter cubed, a mantle of density around 3,200 kilograms per meter cubed, and a crust of density around 2,900 kilograms per meter cubed. Unlike the terrestrial planets, the moon does not have an iron core, which would have a density of around 1,000 kilograms per meter cubed, but it's at least somewhat differentiated. So remember, differentiation was when the heavy stuff sinks to the center and the light stuff comes up to the surface. Because of the lack of a liquid iron core, so the moon does not have a liquid iron core, the lunar magnetic field is weak. However, magnetization of surface rocks indicates that the magnetic field was stronger in the past. Even to the naked eye, the moon obviously has both darker and lighter regions. The lighter colored regions are seen to be mountainous and heavily cratered when seen through a telescope. These regions are known as lunar highlands, like the Scottish Highlands. Yay! Yay! Lunar highlands. These regions are known as the lunar highlands. The dark colored regions are smoother and lower lying. Oh, the lighter colored regions are seen to be mountainous and heavily cratered when seen through a telescope. These regions are known as lunar highlands. The darker colored regions are smoother and lower lying. Some early telescopic observers thought that the smooth, dark regions were oceans and thus called them maria, the Latin word for seas, so lunar maria. Early telescopic observers thought that the smooth, dark regions were oceans on the moon, and thus called them maria, maria. Latin word for seas. Although the maria have long been shown to be solid rock, the inaccurate name has stuck. So apparently, they're shown to be solid rock, but the inaccurate name has stuck. In fact, the maria are not perfectly smooth. They do have a few scattered craters on their surface. They aren't nearly as cratered as the heavily pocked highlands. However, I'd watch Highlander on the moon. The maria are concentrated on the side of the moon facing the earth. Oh, the maria are concentrated on the side of the moon facing the earth. We kind of talked about the craters a little while ago. The lunar highlands are an old surface, largely unchanged since the time of heavy bombardment. So they're gonna see, we're talking about it right now again. The lunar highlands are an old surface, largely unchanged since the time of heavy bombardment with planetesimals. The highland surface is saturated with craters. That is, there is no part of the surface that doesn't lie within a crater. The ages of igneous rocks, either of lunar or terrestrial origin, can be determined by the process of radioactive dating described in the appendix to this chapter. Radioactive dating of rock samples brought back by the Apollo astronauts. So this is some more stuff from the moon landing. Radioactive dating of rock samples brought back by the Apollo astronauts reveals that the typical age of a highland rock that is the time since it solidified from lava, is 4 billion years. The typical age of a Mare rock is only about 3.5 billion years. So there's a difference in the rock ages depending on whether you got it from a highland rock or a Mare. The ages of moon rocks are in marked contrast to the measured ages of surface rocks on Earth, which show a wide range of ages from 0 years for rocks solidifying now at volcanically active sites to 4 billion years for the oldest rocks in geologically stable locations. So the fact that the moon's rock ages have given us 4 billion years or 3.5 billion years, but the Earth has a great diversity of rock ages is interesting. The most obvious features on the surface of the moon are impact craters, roughly circular depressions shaped like shallow bowls with a distinct rim that are the result of planetesimals, and smaller debris hitting the moon's surface. So this is how we get craters, Reese. Remember in that phase of the solar system forming, they called it planetesimals. Basically, little condensations happening, which, remember how all the planets came from condensating of that big gas cloud, and then there were still planetesimals that and other debris that hit our surface, Mercury's surface, Moon's surface. And then remember, it said that some of the surface shapes can get changed again because of like lava coming out, volcanic eruptions and things like that as well, smoothing things over. Crater formation no, so they're talking about it right here. The most obvious features on the surface of the moon are impact craters, roughly circular depressions shaped like shallow bowls with a distinct rim that are the result of planetesimals and smaller debris hitting the moon's surface. So crater formation occurs in 4 steps. We're going to talk about that as well. That occur in rapid succession over a matter of seconds. So crater formation occurs in 4 steps. We're going to talk about these 4 steps. Impact. An object collides with the lunar surface. This can occur at speeds as high as 73 kilometers per second. The local speed limit for any object orbiting the sun in the vicinity of the Earth-Moon system is the escape speed from the sun. At a distance, okay, at a distance, r equals 1 astronomical unit from the sun's center. This is simply v escape velocity, which is 2 g_m sun over r to the 1/2, which is 42 kilometers per second. If the Earth orbiting the sun at a v Earth of 30 kilometers per second has a head-on collision with such an object, the relative speed will be v equals v escape plus v Earth, which is 42 plus 30, which is 72 kilometers per second. The moon is orbiting the Earth at a speed of 1 kilometers per second, so a similar head-on collision with the moon can have a relative speed as high as 73 kilometers per second. So impact is the first step. An object collides with the lunar surface. Next is deep penetration and vaporization. The colliding object will penetrate the surface like a bullet. So it's going at a very rapid speed compared to the speed of the moon. The moon is orbiting the Earth at a speed of 1 kilometers per second, whereas this thing that's impacting with the moon is going at like 73 kilometers per second. So the object will penetrate the surface like a bullet. It is moving faster than the sound speed in rock, which the sound speed in rock is 8 kilometers per second, which determines how fast rock can break up into fragments. As the colliding object buries itself in the lunar crust, it is rapidly decelerated, and its kinetic energy is converted into thermal energy. The released heat vaporizes the object and the surrounding lunar rock, As a specific example, consider a rocky object of radius r equal to 1 kilometer striking the moon at v equal to 73 kilometers per second. If the mass density of the rock is around 3,000 kilograms per meter cubed, the kinetic energy of the object before it hits the moon is 1/2 mv squared. It comes out to be 3 times 10 to the 22 joules, equivalent to the energy released by 10 million megatons of TNT. So lots of energy release as well. The released heat vaporizes the object and the surrounding lunar rock. So this thing that collides at a rapid speed penetrates the surface like a bullet, moving faster than the sound speed in rock. It's rapidly decelerated and its kinetic energy is converted into thermal energy. The spinning ball is going at 1 kilometers per second and the thing is going at 73. Do you understand the difference between the speeds of the things? Okay, third step, formation of crater and ejecta. The hot gas formed by vaporizing. So where that stuff is hitting the surface of the moon, there is like penetration and vaporization from the thermal energy, from that, all that deceleration of that thing in the surface. The hot gas formed by vaporizing the colliding object and surrounding rock will expand explosively, forming a large circular crater where the explosion bursts through the moon's surface. Impact craters are almost always circular, regardless of the angle of impact, because the crater is formed by the isotropic release of energy beneath the surface. So I think here's your question about the 90 degrees. It's not really about the, we're just reading that line now. So the hot gas formed, again, step 3. There are 4 steps of how we make impact craters. Third step is the hot gas formed by vaporizing the colliding object and surrounding rock will expand explosively. So it's this whole process that makes the circular craters. You have to have more patience in order to get through the steps. The hot gas formed by vaporizing the colliding object and surrounding rock will expand explosively, forming a large circular crater where the explosion bursts through the moon's surface. Impact craters are almost always circular, regardless of the angle of impact, which is what you're asking about, because the crater is formed by the isotropic release of energy beneath the surface. Ejecta thrown outward from the explosion will cover the surrounding area, forming what is called an ejecta blanket. Wow. The ejecta blanket may contain glass droplets formed when silicates are fused under intense heat. Thus, young craters may be surrounded by bright rays containing these reflective bits of glass. Wow. The impact described above will produce a crater with diameter around 100 kilometers and depth of 5 kilometers. Fourth step, formation of crater walls and central peak rebound of the lunar crust produces high crater walls and a central peak in the crater itself. The lunar crater Copernicus is a young crater with a diameter of d equals around 93 kilometers, a central peak, and terraced crater walls. It is estimated that Copernicus was formed by the impact of an object with diameter of around 1 kilometer, approximately 0.8 giga-years ago. Wow. Baji? No Baji. So I'm not sure that the impacts have been observed because they might have happened a long time ago. Like this one, rebound of the lunar. Fourth step, formation of crater walls and central peak. Rebound of the lunar crust produces high crater walls and a central peak in the crater itself. The lunar crater Copernicus is a young crater with a diameter of 93 kilometers, a central peak, and terraced. So like terraced crater walls, it is estimated that Copernicus was formed by the impact of an object with diameter of around 1 kilometers, approximately 0.8 gigayears ago. What is your problem now that we discussed about the angle thing? Because you had an issue with the angle of impact, and we talked about how regardless of the angle of impact, the crater is formed by the isotropic release of energy beneath the surface. So what is the issue now? Very large impacts can fracture the lunar crust to a great depth and allow subsequent flooding by molten rock from the mantle. This is how the Maria were formed. Shows Mare Oriental. Oh. Smaller impact craters, Maria, are nearly circular. Apparently the Maria are nearly circular as well. Goodness. The difference in cratering between the relatively smooth Maria with ages averaging 3.5 gigayears and the crater saturated you would see something like impact marks when you skip a stone on the surface or water. Okay. And you would see something like impact marks when you skip a stone on the surface or water. Impact marks. Okay. Isn't that what we're talking about? How the craters were made? Of water, on the surface of water. We were talking about craters on the moon, actually. We're on the section called Moon's Interior and Surface. Why do you think that it was the surface of water? Very large impacts can fracture the lunar crust to a great depth and allow subsequent flooding by molten rock from the mantle. The difference in cratering between the relatively smooth Maria with ages averaging 3.5 gigayears and the crater-saturated highlands with ages averaging 4.0 gigayears shows that an era of heavy cratering took place more than 3.5 gigayears ago. This is about the time the solar system was being cleared of remaining planetesimals and debris after the formation of planets. In addition to the moon, all the terrestrial planets underwent this heavy bombardment. So by the way, this is again talking about what hit the moon and other planets. Heavy cratering happened more than 3.5 years ago, about the same time when the solar system was being cleared of remaining planetesimals and debris after the formation of the planets. A valley. So you're saying like it should look like this. I think what they're talking about is it's getting hit like a bullet at a very fast speed, and then some more steps happen after that impact. So I think you're caught up with the impact step when there is actually like 4 steps of why and how we get these impact craters. And the reference for the book again is Foundations of Astrophysics. This is page 223. So maybe if you read it yourself, you could follow it better. Actually, I will let you read it in just a second when I get up. But basically, I think you're hung up at the impact phase, like you're thinking about it in terms of the angle of impact and all that stuff. But actually, it's about the impact velocity, what happens after the impact, the penetration, the vaporization, the formation, you know, there's more to it than just the angle. The point is still valid. How? That there should be a valley? I don't know how that point is still valid, but okay. In addition to the moon, all the terrestrial planets underwent this heavy bombardment, and all bear the scars to a greater or lesser degree. The Earth seems less affected than the other terrestrial bodies, but this is simply because erosion by wind and water is more The Earth seems less affected than the other terrestrial bodies, but this is simply because erosion by wind and water is more efficient on the Earth and has obliterated craters that formed long ago during the epoch of heavy bombardment. So they keep mentioning this heavy bombardment phase when a lot of planetesimals and debris were hitting things. So the 6 Apollo missions that successfully landed on the surface of the moon returned a total of 400 kilograms of surface rocks. Wow. So this Apollo mission that you guys, some of you don't believe in, returned a total of 400 kilograms of surface rocks from both Maria and Highlands. After study, lunar rocks were discovered to differ from terrestrial rocks in several fundamental respects. All lunar rocks are igneous, solidified lava. There are no sedimentary rocks made of weathered bits of rock cemented together, or metamorphic rocks made from igneous or sedimentary rocks subjected to high temperature and pressure. Lunar rocks do not contain detectable amounts of water. Wow. By contrast, Earth rocks can contain as much as 3% water and nearly always contain detectable amounts of water. The iron in lunar rocks is not oxidized. Ooh! Iron reacts quickly with free oxygen to form ferric oxide, otherwise known as rust. This indicates that the lunar rocks have never been exposed to an oxygen atmosphere. The iron in lunar rocks is not oxidized. Look at that. Lunar rocks don't have their iron oxidized. Iron reacts quickly with free oxygen to form ferric oxide, Fe2O3, otherwise known as rust. This indicates that the lunar rocks have never been exposed to an oxygen atmosphere. Lunar rocks are depleted in volatile elements. This suggests that the rocks of the lunar crust were exposed at some point to higher temperatures than were the rocks of the Earth's crust. Hi, Fuji. Hi, Fuji baby. Oh, Fuji baby is sleeping so nicely and cutely. Hi, baby. I love you. Hi, Fuji baby. The higher temperatures would also explain the lack of water in the lunar crust. It was boiled away. Okay, so now I'll read the comment. You throw droplets of paint at a ball the size of a house. Some droplets would hit the edge of the ball and create a long paint streak, even if the origin of the paint was the same place. I don't know if that analogy is like, I think if you need that analogy to make sense of things, then that's totally fine. But I don't know that's necessarily the right analogy here. Because I think you're still, again, caught up with the angle of impact. When dude, we're talking about something impacting and then penetrating and vaporizing and all those steps that I mentioned. It's not just about which angle it hit. Like this, the colliding object will penetrate the surface like a bullet. It's moving faster than the sound speed in rock, which determines how fast rock can break up into fragments. As the colliding object buries itself in the lunar crust, it is rapidly decelerated and its kinetic energy is converted. What is your analogy for the kinetic energy that's converted to thermal energy? There's more processes here than whatever the fuck you're saying, man. That's the part that I'm missing, which is that I was saying all the steps and you just don't care about after step number 1, which is impact. The next step is called deep penetration and vaporization. The third step is formation of crater and ejecta. The fourth step is formation of crater walls and central peak. Hi, Shinobi. Okay, so apparently lunar rocks are depleted in volatile elements. This suggests that the rocks of the lunar crust were exposed at some point to higher temperatures than were the rocks of the Earth's crust. The higher temperatures would also explain the lack of water in the lunar crust because it was boiled away. The moon shows no evidence The moon shows no evidence of large volcanoes similar to those seen on the Earth, Venus, and Mars. So Earth, Venus, and Mars have these large volcano evidences. Moon does not. However, features called rilles, R-I-L-L-E-S, provide evidence of past lava flows on the moon. Rilles, whatever that word is, are sinuous valleys. Oh, there's a valley now, Reese. He really wanted valleys on the moon. Rilles are sinuous valleys that are the remnants of lava rivers. Similar, although shorter, lava channels are seen on Hawaii, where hot lava flows between levees of igneous rock. So, if the lava drains from the channel before solidifying, an empty rilli is left behind. Rilli versus maybe rill, I don't know what the word is. Apparently there's also these other features called rills or rillies, which provide evidence of past lava flows. So maybe the paint thing that you were saying have to do with these lava flows, but they don't have to do with the extremely fast impacting things that we want valleys from impacts at an angle, not lava. No, yeah. We can agree to disagree on that part because you only are thinking about the impact and the angle of impact and not the other steps. I would like for you to come up with an analogy for the conversion of kinetic energy to thermal energy after something hits the surface of the moon like a bullet, which was part of, I think, the second or third step, which apparently you just want to ignore, which is fine. So the entire lunar surface is covered with a layer of dust and rubble, most of it simply lunar crust that has been pulverized by impacts. This layer, the regolith, is 2 to 10 meters thick. The top of this layer is only loosely packed, and the Apollo astronauts left footprints a few centimeters deep in it. Because, because the crater is formed by the isotropic release of energy beneath the surface. Do you know what isotropic means, since English is your first language? And you're correcting my pronunciations? Look up isotropic. Do that. What time is it? The crater is not just formed magically upon impact. There are some more steps. So, third step. See? The first step was impact. Crater's not made yet. The second step is deep penetration and vaporization. Crater's not made yet. The third step was formation of crater and ejecta, which is the hot gas formed by vaporizing the colliding object and surrounding rock will expand explosively. So there is even expansion and explosiveness of expansion that is nothing to do with your paint and ball. Forming a large circular crater where the explosion bursts through the moon's surface. Impact craters are almost always circular regardless of the angle of impact because the crater is formed by the isotropic release of energy beneath the surface. Ejecta thrown outward from the explosion will cover the surrounding area, forming what is called an ejecta blanket. So there's some more features too. The ejecta blanket may contain glass droplets. We talked about that. Formed when silicates are fused, you know. It has more detail than what you are envisioning. So, the entire lunar surface is covered with a layer of dust and rubble. Most of it, so we have now moved on. We're still in those valleys now. We're now talking about the valleys. The entire lunar surface is covered with a layer of dust and rubble. Most of it's simply lunar crust that has been pulverized by impacts. This layer, the regolith, is 2 to 10 meters thick. The top of this layer is only loosely packed, and the Apollo astronauts left footprints a few centimeters deep in it. We have said nothing about the moon's atmosphere so far. This is because the moon has virtually no atmosphere. Its slow rotation makes the daylight side much hotter than that of the Earth. Oh, wow. Because of the moon's low albedo, which is around 0.07 for the dark Maria, the daytime temperature of the lunar crust is close to the subsolar blackbody temperature of around 395 kelvins. The combination of high temperature and low surface gravity does not permit the moon to retain common atmospheric molecules. The combination of high temperature and low surface gravity. So it's not just about surface gravity, it's also about the high temperature, which does not permit the moon to retain common atmospheric molecules. Wow. I don't think I yelled. It's a mostly healthy debate. Implies the actual object makes... Yes. Yes, I think we agree now. This implies that the actual object makes no impact crater. Yes, because the actual object, upon impacting, impact is the first step, then there's some other steps. That actual object, all it does is impact the moon. Then there's other things that makes the crater. Other steps. The first step of impact, object collides with the lunar surface. That's the first step. So if you're saying that in that very first step, the crater is not made, you would be correct. Thank God we finally agree on something. She's gonna start yelling. So I think we finally agree. That very first step does not make the crater. No, Rome was not built in a day. That crater was not built in the first step, which I've been trying to communicate about 400 million times. There are 4 steps. 1, 2, 3, and 4. I don't know if you can count or understand English, but there are 4 steps. Thank you. Astronomer. Okay, I need to get more water. You can say all of this to a British guy, right? Belgium guy. Sorry. Oh. I'm gonna have some ginger ale. Yes, I've decided to be more harsh because of your origins. In that sense, I am that thing that you are thinking about. I'm like, do you understand English? Do you know how to count? No? Too bad. Do you understand words? God, this person will drive me nuts. Hello. Hi, Fuji Baji. Moon landing. First of all, he doesn't even believe in the moon landing. That's actually very common there. That's how you know we're mad. When we're like, do you even understand English? Because English is like the easiest language we speak. So in India, the easiest language we speak is English. So if we're saying, do you even understand English? It means that we think you are something. A little bit like this. Yes, that's correct, Reese. He can wear what he wants. What do you mean? What do you mean? Yes, he can wear his mom's clothes. But do you even understand English? Do you even know? Is the school system in Belgium so bad that it hasn't taught you about the moon landing? You don't even believe in the moon landing, and you're like, the impact craters, why are they all the angles? I'm like, dude, they're circular because of step 3. Do you even know what an angle is? Since we have established that you don't understand English. So like, do you even know what an angle is? This electrician is gonna kill me. God! Let me charge my phone. Freaking. Okay, yeah, Doro understands angles. But this Belgian guy, he does not. Indeed, he does not. Let me show you the page. I don't believe in the moon landings. Wow. My college actually did state it has been debated. Well, what the frick college did you go to, Doro? Here. You can read the book here yourself. See? First step, impact. See how there are more steps if you can count? 1, 2, 3, you know? Counting, do they teach that in your school system? If I say that, I dox myself. Okay, yeah, that's fine. Don't say that. These impacts have been physically observed. Oh, have not been. You know what's not been physically observed, Reese? Your intelligence. And your ability to read. Oh my God. You know what? It's so cold down here. Don't go for my Barbara. She's a very good lady. I'm Facebook friends with her. Don't you dare go for Barbara. You've done enough bad things today. Enough bad things. I know. The analogy he brought about paint. I mean, he doesn't believe in the moon landing. And I'm trying to get him to read sentences here, which I don't know if he can do that. And the analogy was extremely weak, if I may say so myself. You know what? The moon is very special to me. I think we're gonna break up over the moon. We are no longer friends, and I no longer care about people who can't read. We're no longer friends, that's right. gonna tell my friend James that there's always this guy called James who's constantly wearing his mother's clothes. There's the guy who's constantly wearing mother's clothes. The guy who can't read. The guy who doesn't understand English. You know, when you don't believe James, you're just making him more, I don't know, saying those things. Oh. I'm kind of sad. I liked being her friend. Never. Never, ever. All right. We will, let's see, I'm charging the phone. Astronomers have long wondered why the Earth has such an anomalous, look at that. There's some Maria for you. Or not Maria. This is a Hadley Riley, a sinuous Riley with a total length of 120 kilometers. He's obviously trying to get you to laugh. I don't think so, Doro. He is vicious. He made me laugh. I should thank him. Gave me relief from a stressful day. Oh yeah, I'm glad you got relief from a stressful day, Doro. Oh, that's good. I laughed too. That's true. But Reese is vicious and we are never friends. And Doro, I'm glad you are not as stressed out anymore. What happened? Why were you stressed? Astronomers have long wondered why the Earth has such an anomalously large satellite. So did you know that our moon is one of the biggest moons in the solar system? Of the other terrestrial planets, Mercury and Venus have no natural satellites. And Mars has 2 tiny irregular satellites. The moon, with a radius equal to 0.27, the radius of Earth, is remarkably large in comparison with its parent planet. Over the course of time, many hypotheses for the moon's formation have been proposed and then discarded. Wow. Now, Seth. Hello, good afternoon. Hi. My job is stressful. It is what it is. I agreed to take it, so it's whatever. Hi, now, Seth. So there are like a bunch of different hypotheses. The fission hypothesis states that the moon was flung away from the equator of a very rapidly rotating proto-Earth. One problem with this hypothesis is that the moon is not in Earth's equatorial plane, as you would expect in such a scenario. Another problem is the observed difference in chemical composition between the moon's crust and the Earth's crust. In this scenario, they came from the same material. So there are some issues with some of these hypotheses. Wow. The capture hypothesis states that the moon formed elsewhere in the solar system, ventured close to the Earth, and was gravitationally captured. The main problem with this hypothesis is that to go from a sun-centered orbit to an Earth-centered orbit, the moon would have to lose a great deal of kinetic energy. All the mechanisms proposed for breaking the moon, passage through a dust cloud, interaction with a third body, are highly improbable. The co-creation hypothesis states that the Earth and the Moon formed side by side at their present distance from the Sun. The main problem with this hypothesis is the very different chemical compositions of the Earth and the Moon. Why did the high-density Earth get so much more iron than the low-density Moon if they formed in the same place from the same population of planetesimals? The currently favored explanation for the formation of the moon is the giant impact theory. This scenario states that just over 4.5 billion years ago, a protoplanet roughly the size of Mars struck the proto-Earth. Here, let me take this. I think it's charged. Enough charging for now. Let me read this part while sitting down. Hi, Fuji. Look where Fuji is. Hi. There's Fuji. Where did Reese go? Hi, Mick tonight. Are you looking for an uneducated person to debate with? I just read on our physics that we're debating the moon landing. I'm uneducated. I didn't mean you. I meant that he's in the wrong place. But actually, he's in the right place, given some of the people who attend this live. Right, because you don't believe in education either. If if education said that there was a moon landing, you'd probably be like, oh, I don't believe it. God forbid. God forbid. I'm too cool for school. Okay, that's fine. Actually, I think it is sad. A lot of things are not really outreached to people from the various scientific projects. The currently favored explanation for the formation of the moon is the giant impact theory. This scenario states that just over 4.5 billion years ago, a protoplanet roughly the size of Mars struck the proto-Earth. Mars is 9 times the mass of the present moon and 1/9 the mass of the present Earth. Both the proto-Earth and the colliding protoplanet were differentiated, containing rocky mantles over iron cores. The impact was not head-on, but oblique. Reese will love this oblique impact. Computer simulations reveal that during the impact, the rocky mantle of the colliding protoplanet was ejected into an Earth-centered orbit, eventually cooling to form the moon. So this is indeed a theory. The iron core of the colliding protoplanet sank to the center of the Earth and merged with the Earth's core. Thus, the moon ended up being made almost entirely of rock, while the iron content of the Earth was enhanced by its cannibalism of the colliding protoplanet's iron core. We don't know what dreams are, what consciousness is, or how the brain generates it. We don't even know how anesthetic works. Hi, Rupesh. Giant impact theory. Wow. This is cool. This is really cool. So, over 4.5 billion, a protoplanet roughly the size of Mars struck the proto-Earth. Both the proto-Earth and the colliding protoplanet were differentiated, containing rocky mantles. Oh. The iron core of the colliding protoplanet sank to the center of the Earth and merged with the Earth's core. Thus, the moon ended up being made almost entirely of rock. This is so cool. 4 frames at intervals of 4.2 minutes of a computer simulation of the impact that ejected the moon in the upper left panel. Look at this. Here's the simulation of the moon forming. In the upper left panel, the arrow indicates the initial velocity of the impacting protoplanet. I mean, I think it's all very interesting, and it's definitely good to think about it more. That's for sure. It's also the work that you would put into it, you know? Like, it's one thing to I think there needs to be more work, basically, that goes into the exploration of these things. 4 frames at intervals of 4.2 minutes of a computer simulation. This is so cool. So, like, there was more differentiation. Exploration. Like, I think it's good to have a curious mind if you're gonna put, especially if you're gonna put the work in to explore the questions that you want to explore, you know? And keep an open mind. So, Proto-Earth, wow. They're saying that this collision, wow. So part of the Earth's mantle look at this. Let me rotate the camera. Look at this. They're saying that some collision happened with another planet, also with an iron core. Then differentiation started happening where the iron core settles towards the center, and then part of the outer layer of the Earth, like the mantle, is the one that is making the moon. Let me read that again. Sometimes I have to read a thing multiple times for me to fully get it. The rocky mantle of the colliding protoplanet. I see, that's wacky. Yeah. The rocky mantle of the colliding protoplanet I read everything twice or 3 times to comprehend it. Yeah. Yeah. Depending on what it is, how new it is, I need to read it multiple times. For sure. Helps to read it multiple times. I can't read. The rocky. The impact was not head on, but oblique. Like Reese's paint. And then simulations reveal that during the impact, the rocky mantle of the colliding protoplanet was ejected into an Earth-centered orbit, eventually cooling to form the moon. The rocky mantle of the colliding protoplanet was ejected. I'm not so sure how it was ejected. Or you know what? It could be because the Earth is rotating, revolving, all that. Reese's paint. Reese's Pieces. Reese's paint. The iron core of the colliding protoplanet sank to the center of the Earth and merged with the Earth's core. Thus, the moon ended up being almost entirely of rock. Made almost entirely of rock, while the iron content of the Earth was enhanced by its cannibalism of the colliding protoplanet's iron core. That is really cool, actually. That's so cool. But see, the person or people who might be working on this computer simulation to show whether this is true or not, or like what are the conditions you need for this to happen, you know, that is exploration. That is research. You can have an open question about something that you may not have observed, and so you don't really know it. But then you can explore it, you can research it by doing these simulations and doing this work. A lot of work goes into even the exploration and the research. So even if you don't know something, you can still do a lot of work. And generally speaking, a lot of work is done before people write these books, you know? And so right, and that effort is really cool. We do similar things at my job, obviously different subject matter. And so, yeah, basically, let's just say Barbara had a very good reason before she would write something in a book like this, because this is a textbook. So I'm all for the open conversations of research topics that are still like very much a research topic. And people definitely sit and debate these at like the universities and things like that too. And like if some paper came out and it's not really super understood yet, then that's different. But if it makes its way into a textbook, that's generally much more well understood. But it's not always the case that just because it's in a textbook, it has to be correct. So I will say that it's always good for sure to keep an open mind. You want to learn the topic and try to understand what is being said and what is the basis of it. But it's not to say that for sure, just because it's in a textbook, it's correct, for sure. So I will say that. But at the same time, we should try to follow the material that's being presented. I drink paint. It helps me to believe that the moon landing happened. So yeah, indeed. But yeah, there are various different levels of effort that goes into exploration and research. And a lot of effort has gone into saying the stuff like what we're saying right now from a textbook. So I appreciate that. Okay, now, but it's so interesting what they came up with. Isn't that so cool that they think that there was some other planet sort of that impacted our planet and even contributed to the iron core of our planet, and somehow the mantle part kind of got ejected out, which ends up being the moon, because the moon doesn't have that same core or the same diversity of rock like we do. That's incredibly interesting. I do think that so long and short of it also is that I think even our solar system is actually filled with mysteries. There are definitely still mysteries in our solar system. Because some of the things, there's no real way to like confirm it, right? So to some extent, it is mysterious, but I feel like that too is kind of exciting, because if you want to go and explore it and research it further, you can. The opportunity is there. So yeah, I think I think that's really cool. There are definitely mysteries, but some things are better understood than others. Generally speaking, if something is in a textbook, it's pretty well understood. But there's no guarantee that it will always be correct. But generally speaking, it is. Most of the time. Hi, Fuji baby. Shona Bablu. All right. Well, I think that was the discussion today. We will continue our topic tomorrow. We will continue with these types of topics tomorrow. I don't know. Textbooks put me to sleep. Well, we might just be a cure for some people's insomnia then. We are definitely referencing textbooks and things like that, and we're discussing these topics together. Thank you so much for all your participation. We will continue to chat for a little bit longer and wrap up the discussion of today. Thank you so much for being here for the whole live. If you're seeing this as a video upload, do leave a comment, and we can continue to debate all kinds of things with the moon here in the chat today. No, a live is different. I mean reading one alone, especially in class. Yes, right, correct. So we but you know, we take pride in people's sometimes this content that we do here falls under soothing, peaceful, relaxation content. Indeed, when we read about the moon or the earth or astronomy from referencing textbooks, people do fall asleep to it, and it helps them with their insomnia. And other people sometimes want to engage more in the conversation, and there's even sometimes certain arguments that can happen, like today. But all in all, I think we have a pretty good time, and we can continue this chat, and We thank everybody for their active participation. And here is Baji taking a nap. Sure, I'm one of them, but tonight was wild. That was funny stuff. Right? I know, tonight got a little bit out of hand. Oh my gosh, I think, yeah, it became parental guidance advised. PG-13 level of verbiage was used today. Indeed. Indeed. Where is Reese now? He has probably fallen asleep after creating havoc in the chat. But where is that? Where is that monkey now? I'd say go all in on that, but the problem is, oh, I was talking about someone else. If you weren't, I didn't realize you were still here, Reese. I didn't realize you're still here. Gosh. If you weren't so, I'd say go all in on that. What, the argument? Oh my God, I don't like it at all. I don't like it at all. But the problem is you got to be able to not understand basic problem solving and conversation. So for you, it would feel forced. Yeah, it's hard. It's hard to belong to society. Monkey Christ. I don't know where you're getting monkey. I was speaking to someone else in the house. I didn't realize you're still here. Hi, Fuji. Hi. Mikey! Bullocks. I will watch later. Mikey! There's now a comedian as far as a physicist, as well as a physicist in book/cat tuber. Do you even understand English? Orchard comedian. Nothing mean, it was all hilarious. You're mean. You're mean. Tortured comedian. You're not tortured, you're rich. Can't be tortured. Height of torture. In the moon landing. Height of torture. You had a hunch, you didn't. $1 million. Hi, Key. It's 3 million to be monetized with the shorts. Reese is saying, well, I won't come in the lives anymore, but I thoroughly enjoyed coming in here and meeting you guys. Much love. Are you serious? Well, it's all your fault. Is it nowadays you have to make 1 million views shorts to get monetized? Well, you need 3 million short views. $3 million short views. She can mock me the whole next stream. I didn't mock him. I was simply responding. I didn't do anything bad. She can mock what I said the whole next stream. I don't mock anyone. I don't mock anyone. I don't mock anyone. You didn't, just a point of phrasing. You challenged what I said. I'm never returning. No, please do return. emoji. Is Reese still here? Reese! You know what? Let him be mad. I don't care. Bye, Ben. Thank you. See you. Problem is, I don't come in here wanting to start peaceful arguments. But I guess I gotta learn to want to now. I mean, I think mostly there is peace. There's sometimes like crazy chat, but I think it's mostly peaceful. Reese's fight. I will avenge. Capri. Well, I can hold a grudge too. I will continue to hold this grudge now forever. Before I go over the night, yeah, that's. confide. Word. That's right. Word. You have the Indian girl voice earlier. Since English is your first That was so freaking funny. That was too funny. Rewind. I may rewind to that and watch it tomorrow. That was too funny. Oh, all the steps. No, they're multiple. Step one. It's okay, Reese. Miss you. Come back. Come back and fight. Reese is still here reading and listening. Favorite planet is TOI? Come back and fight, Reese. Or no, Reese is peace now. Reese is at peace now, knowing he is wrong. Reese is at peace, knowing he's wrong. No peace, never peace. You were hilarious. Literally got me to shut down my PC and participate. Upload soon, I will watch later. Thank you, Heike. Upload soon, I will watch later. Thank you, Heike. Sorry, yeah, we're still fighting. That's why it's not uploaded yet. Reese is gonna come in and troll on your next live. Are you working tomorrow, Doro? I am. Thank you for your support. Thank you for your support. And you too, Reese. I was gonna listen and drift to sleep. Instead, I hear about moonlands. Tomorrow, you better come with better questions, please. This is people with education and jobs. This stream is more calm and cerebral, so it was funny as heck. And I like cerebral and cereal.
Okay, I found this on the web for cerebral. Check it out.
Oh my god, Google, stop it. For Siri. Jesus Christ. Cerebral is good. Cereal is good. Oh, because I said that other word, which we eat with milk, that's why Siri is doing what it's doing. Siri, shut up.
Okay.
I love it. I stopped trolling people on the net, so to hear that come back here is hilarious to me. As well as my bud Grimace. Even he texted me about it. Did he? He sure did. We were all laughing. This is a whole conspiracy. He's your friend? I didn't know he's your friend. I know Grimace in real life. He came in for cats. When he goes off though, I don't condone that. Holy moly. Wow. Oh good, thanks for coming. Hi Fuji Gulay. Reese, miss you. Hi, Fuji. Hi, Ram Candy.